Let's now look at this 2005 exam question. We're told that we have a rocket ship, there's a container within it, and it's viewed through a window by Sam, an astronaut who's floating freely through space. Sam observes the rocket ship travelling past a constant speed of 0.2 times the speed of light, so 20%. The dimensions of the container as measured by the astronauts inside the rocket ship are. Now they've noted that the length, width, and height are the proper length, width, and height respectively. And that's because someone within the rocket ship, they would be stationary with respect to that cube, even if that cube is moving from Sam's perspective. That person within the rocket ship is always stationary with respect to the cube, so they measure those proper lengths here. So the question asks us, which of the following options A to D best describes the dimensions as observed by Sam? So Sam is no longer going to be measuring a proper length. He will only ever measure a contracted length, a shorter length, but only in the direction that is parallel to the motion. So that means only in this direction here. So that means the only length that's going to change is going to be this value of L0 here. W0, or the proper width, and the proper height, H0, are going to remain the same because they are perpendicular to that direction. It is only a length that is parallel to the direction of motion that becomes contracted. H and W0, good. Okay, so it looks like we're narrowing down our answers to B and C, because I notice A has changes in W and W0, W and W0 and H0. And this one here, although it says the height is equal, the width is not equal. So we've narrowed it down to B or C. Now we basically need to know, is Sam going to notice a shortened or an increased length? Well, pro tip, you're never going to have a situation where someone is going to notice an increased length. The proper length is the largest possible length. So that means Sam is going to measure something that is a shortened length compared to the proper length. So that needs to be the answer B. Don't accidentally do the answer A because we've already ruled it out due to the width and the height respectively. Okay, we have a 2004 sample exam question. We're told that Robin and Chris are playing in a gym inside their personal glass rocket ship, as one does. That sounds like an excellent construction. Robin throws a basketball as shown below. All the distances are marked on the diagram and they're measured by Chris. So if we're talking about things being measured by Chris, this length here, 3 meters, and this 3 meters, these are both proper lengths. Perhaps we'll call this the proper height, and we'll call this one just proper length. So we see that we've got an astronaut, Fred, is floating freely in space. He observes the rocket ship travelling past him at a constant speed of 0.2 c. That's weird, another 0.2 c example. What is the horizontal distance from Robin to the base of the basket, so Robin is the one currently shooting the basketball, as measured by Fred? Okay, so that is this length here, and as we mentioned previously, it is parallel to the direction of travel. So we know that this is going to be a contracted length, and we're going to have to use our contracted length formula. We're not told the value of gamma, so let's perhaps calculate that first, and then we'll substitute it into our equation. What would be really handy is having some different values of gamma in a little table on your note sheet, but just say you didn't have it, let's go about calculating it. So to remember to find the value of gamma, we're using this equation here. We're going to substitute 0.2 c as V. We're not going to substitute in the value of C for reasons you'll see, see in a moment. So we've popped in this value now. It's really important to put the 0.2 c in brackets because you're not just squaring the c, you're squaring the 0.2. So let's now go ahead and we'll just deal with this V squared over C squared portion before we continue on. Okay, this is the power of not substituting in the value of C squared here, because if you do 0.2 squared, you get 0.04, and now it's just a matter of cancelling off these C squareds. So now we're just going to have 1 over the square root of 1 minus 0.04 to put into our calculators. Okay, putting this into our calculator, we get a gamma value that's not a huge amount larger than 1, but we still need a few extra digits here. I'm going to note down a few extra ones on my page, but I'm going to keep the value of gamma in my calculator for later. We're now going to calculate that contracted length measured by Fred, who is not stationary compared to the spacecraft there. And that is equal to the proper length, which was previously mentioned, divided by that value of gamma. So the proper length, that was the one we circled there, 3.0 meters. divided by this value of gamma that we've kept in our calculator. I'm just writing a couple of digits there, I'm not rounding. Alrighty, the contracted length that is measured, we need to do this to, I think, 2 sig figs? Yep. Oh, 1 sig fig according to this one here. 0.2 C. I think if we do it to 1 sig fig, it's not going to be evident, so it looks like in this question here, we're going to have to do more sig figs than we would normally use, because we use the fewest number of sig figs provided in the question. We're going to do 2 here, otherwise it looks like there's been no length contraction. Now it says, which one of the following A to D gives the vertical distance from the floor to the basket as measured by Fred? Again, Fred is the external observer. We will notice though, that measurement they were talking about there, that was the proper height that we spoke about. That is not parallel to the direction of motion of the rocket. That is perpendicular. So this is a trick question. It's going to be 3 meters, that it does not contract. Now this answer, talking about the distractor answers that we've got here, this answer could never be right. We're never going to have a length larger than the proper length. You might have thought, if you forgot you were talking about parallel motion, that it might have been this answer here, but again, it's not, and I don't know what the 2.4 is doing. Maybe if you made an incorrect, if you substituted things in incorrectly for gamma, I suppose, you could definitely examine that yourselves. Let's now look at this 2006 exam question. Apparently I've altered it slightly. I can't remember the alteration, but still worthwhile looking at. We've got 2 space travelers, Chris and Bob. They're in rocket ships that are traveling towards each other with a relative velocity v. That's close to the speed of light. Cannot be the speed of light though. So Bob experiences themselves as being stationary and sees Chris moving towards them at a velocity of v. Conversely, Chris sees Bob moving towards them at a velocity of v. They agree to measure the length of Chris's rocket ship using 2 methods. Chris measures her ship with a meter stick and gets a value of L. Bob measures the length as L dash. This is not representative of proper length and contracted length. They're just trying to represent 2 different lengths that are measured here. Although both measurements L and L dash are correct, one of them is known as the proper length. Which one is the proper length, and explain why this is so. So just so you know, in this particular year, only 53% of students got 2 marks for this. So number 1, we need to identify who's correct, and we need to give a reasoning for this. So it's really important with these questions to use the number of marks as a guide, but also don't waffle and don't restate the question or worry about using complete sentences. It would be silly to go into a discussion of why both of these are valid lengths in the frames of references, respectively. Again, proper length isn't saying correct length, it's just a definition in physics, and it's the length of an object measured when stationary compared to that object. Using what we just discussed there, who is stationary with respect to the rocket ship? We were wanting to measure Chris's rocket ship, so that means we need to go in Chris's frame of reference to find the proper length. So let's literally do what we were talking about there. We need to identify who measured the proper length, and we need to explain what the proper length is. Remember, this one is examining that you can determine what proper length means and that you know it doesn't mean correct length, because as I mentioned, both lengths are correct. No point saying that in your response to the question because they've already outlined it there. But also it's not really answering the question. So the examiner's notes say that most students were able to identify Chris's measurement as the proper length. So about 73% of people were at least able to get 1 mark or more. But there were many students who weren't able to determine that. So it is really important on your note sheet that you have a definition of proper length and perhaps an example diagram like this. And again, one thing to talk about, that proper length, if we're measuring the length of the spacecraft, I don't know if they're doing the body or they're including like the tail region, but that is, well, it doesn't matter whether it's proper or contracted length because we're in Chris's frame of reference. We're not talking about Bob's frame of reference and the contracted length there. Spoke too soon. It says, which of the following is the correct relationship between the length of Chris's rocket ship as measured by Chris and Bob? So, Bob is going to measure a shorter length because that length that we just mentioned, that's parallel to the direction of motion, so Bob is going to see a contraction. So we can immediately get rid of this answer here. Now, they've written this equation slightly differently. We're used to seeing the notation of the contracted length equals the proper length divided by the value of gamma. we need to basically translate in this question here, because we were told that L dash was Bob's length. This is the contracted length. And in our formula, we usually use L for that. And they said that Chris measures it to get a value of L. This is the proper length in our formula. So usually we use L naught. So we need to be especially careful when we look at our formula. I'll notice they also have substituted in the value of gamma here. Remember, gamma is that 1 on the square root of 1 minus v squared over c squared. So let's put in the value of gamma, and then I reckon right at the end we'll change the value. Instead of L and L naught, we'll do the values, the variables that they used above to make sure we can answer the question. So for reasons you'll see in a moment, I've written it as L naught divided by, and as I said, this is the value of gamma here. Instead of writing it as dividing by a fraction, I could multiply by the reciprocal. So I'll change that to instead 1 over, and I could just write that as this, and I'll change this to a multiplied now. So in this question, instead of L, we need to write L dashed, and instead of L naught, we need to write it as L. So L dash is going to be L times 1 minus, didn't need the times sign there, v squared over c squared. Do we have an answer that looks like that? Not currently. At the moment, you might think that that's our answer, but we very carefully determined which was L and which was L dash. They've got all of the formulae in terms of L. So if we were to rewrite this in terms of L, we would need to divide both sides by this surd that we've got here. That would be L dash on the square root of 1 minus v squared over c squared. I reckon if I weren't really careful there, I might have chosen C as my answer, and I'd love to see some data on that. Ooh, I just looked up the data, and it says 41% of people got this wrong, so I'd wager that a lot of people chose C. It's not showing me that particular piece of information. So, our answer, if we've got L equals L dash divided by that surd, it's actually going to be B as our correct answer. Okay, really nice question here. I'm not actually sure where this is from. It says the relativistic effects are not easily detectable in everyday situations. At what speed would an object have to be moving for a 1% change of 1% in its length to be observed? To begin to consider this question, let's look at the length contraction formula. So we're going to be using that, but I want to loop back to thinking about this change in 1% for a moment. If we have a change in 1%, then we're expecting the length to be 0.99 times the non-contracted, or the proper length here. So we'd be expecting L to be equal to 0.99 times L naught. So there's a couple of ways you could do this next bit here, but if we directly substituted this here into our length contraction equation, again, you could do this slightly differently. Let's see what happens. So instead of L, let's put in 0.99 L naught equals L naught over gamma. We can now cancel off that value of L naught from both sides. So we can see that 0.99 has to equal 1 over gamma. That means gamma would need to be 1 over 0.99. Why is that so helpful? Well, we could substitute this value into our equation for gamma. There's a little bit of algebraic manipulation involved in what I'm doing at the moment, and you'll see the result at the end. For those of you who are not as confident algebraically, having a rearrangement for this on your note sheet could be exceptionally useful. You'll see that I expanded out the 1 over gamma squared to be 1 squared over gamma squared. I actually will reverse that a little later on because we already had an expression for 1 over gamma being that 0.99. So to get that v by itself, we need to take the square root of both sides. And in the last step you'll see me do in a moment, I take that c out of that surd. Alrighty, so you could rearrange this equation a bit, and if you wanted to keep going mathematically and deal with the fact that you've got a gamma squared inside of there, you could. But for the purposes of what we're doing at the moment, I don't think it's necessary. So, I originally left it as 1 on gamma squared, and then I changed it to 1 squared over gamma squared. I think it would actually be useful to leave it as 1 over gamma squared. I originally did that because we originally were told that 1 over gamma was 0.99. So perhaps let's revert to that. So V is going to equal C times 1 minus, and we said 1 over gamma was equal to 0.99. And we need to square that. Okay, so if I just calculate the third portion, if I do 1 minus the 0.99 squared, then I get the velocity is equal to, let's do this to 2 sig figs, I'm just arbitrarily choosing, or maybe I'll do a few extra, 1 point. So I've left it in terms of C. The question hasn't specifically said what unit we'd need this in. If there was a box at the end that has it in terms of C, we could have left it like this. So that's 14% of the speed of light would have a 1% change in length. If they wanted it in terms of meters per second, we'd need to do 0.14 times 3 by 10 to the 8. And I'll leave that for you to look at. It's more the process of what we did here. Really determining this initially was really important, and thinking about how we could relate that to gamma to determine the value of the velocity there. Having a rearrangement for the velocity, such as in this example here, would save you a huge amount of effort in the future. So putting a rearrangement like that, or if you're mathematically inclined, you might like to clean up the inside of the cert a little bit, putting something like that on your note sheet, very valuable. Okay, I couldn't help myself. I've done 2 other possible algebraic rearrangements here. Remember, when we talk about doing square roots in physics, I always mention we should think about the positive or negative, but for this we're just interested in the speed, not the direction. So these are other rearrangements that could work. The one that I had in the blue box was most useful here because I already had a value of 1 over gamma was 0.99. I've noticed with a lot of these questions, the name Bob comes up a lot. We've got alien astronauts are traveling between star systems aboard a cube-shaped spaceship. Interesting. The sides of the cube along the x, y, and z axes measure 3.2 by 10 to the 3 meters in the spaceship's frame of reference. So these refer to the proper lengths. So the spaceship passes Bob, who is on a space station. We're told the value of V, and very kindly they've told us the value of gamma for that value of V. In the table below, we want to determine the dimensions of the cube-shaped spaceship as measured from Bob's frame of reference. So remember, he's going to be measuring L, which is the contracted length. Oh, fell off the screen a little bit. So we need to consider, we've got the axes here. The only axis that's going to have any length contraction is going to be that z-axis. So that means with the x-axis I meant to say, not z-axis. I literally drew it, but I said something different. That means the y and the z, we can immediately put in that length that they listed here. So it's 3.20 by 10 to the 3 meters, and that's in both of these instances. So we're going to have to use length contraction and the value of gamma that they gave us in the question to be able to determine the length in that x direction, which is parallel to the direction of travel. Okay, giving this answer to 3 sig figs, we're going to have 451 meters. Now, we need to explain exactly the reasoning we use to be able to put these answers in here. We need to explain that the x-axis is parallel to the direction of motion, so we need to consider that contracted length, and that the y and z axes are both perpendicular to the direction of motion, so no length contraction will occur. So to really make sure we've answered the question, I've specifically referenced the axes that they've told us here. I've not just given a broad statement of length contraction only occurs parallel to the direction of motion. I've specifically and explicitly said that's the x-axis here, whereas the y and z are perpendicular, therefore unchanged. Okay, that was the 2019, Northern Hemisphere exam. This is the regular exam here. We've got Joanna is an observer in Spaceship A. Maybe I'll just note that Joanna is here. Watching Spaceship B fly by. We're told the relative speed and the value of gamma. Thank you. She measures the length of Spaceship B from her frame of reference to be 150 meters. So this is the contracted length L. She cannot measure the proper length because she is not on Spaceship B, or at least stationary relative to Spaceship B. We know that 150 meters is the contracted length. So we know at least that it can't be the values of A or B. It needs to be a length greater than that. The proper length is the largest possible length. Using the value of gamma and using our equation, this currently has L as the subject, so we need to change that to L naught, so that'll be L times gamma. And that makes sense, gamma is always a value greater than 1, so we're multiplying the length by something greater than 1, so the proper length is going to be larger. As we said, proper length is the largest length we can have. So the contracted length was 150, the value of gamma was 3.00. So that's going to give us the 450 meters that they've given us here. Excellent.